Okay, welcome folks to our office hours. Just a section here. I'm making sure we're up and running. We've got a bunch of great questions today. The first one is from one of the students that wanted to see how we implemented the Java tip calculator and the algebra tutor. We have a little example here. Oops, hold on, let me. Okay, that's not behaving itself. All right, sorry about that.
All right. Okay, why is that blinking?
I don't know. Is that blinking for real? Let's see if it, yep, it's totally blinking for real. Okay, there we go. A little bit better. Okay, so this one is pretty simple. It's a real simple scanner, and it does two calls for input from the user. The first one is it does a little prompt, and notice that we used print instead of print line. So this one says enter the total bill amount, and the cursor doesn't go to the next line after that. Then we take the input as a double. So in this case, the double is the amount, the total bill for the table, and that gets the next double number, the next floating point number, and takes that as input from the user when the user hits enter. The next prompt is another print, and this one, again, doesn't go to the next line when this is printed out, and this takes the service level as an integer as input. So the next piece, the user input dot next int, takes one non-floating point number from the user when they press enter. And if they put, remind me, will it throw an error if the user inputs a decimal, or will it just take?
So if they input a decimal, it'll probably just read up to the decimal point.
Okay.
And leave the decimal point in there.
Okay, so you don't have to do any special checking as the programmer or whether or not they gave you an int or a floating point number. You can just take it as is, and that works well. Cool. And then I have a little calculation here where I take the service level that we got from the user and divide it by 10. That gives us a number between 0 and 1 of the service level. It's kind of a scaling factor, right? So it's like if I entered a service level of 5, then I would get 0.5 from this calculation, and I multiply that by the maximum tip. So they would get half of the maximum tip, which is 0.3 of whatever the total bill is. And that's what that little calculation there does, is it gives us the tip in the number, it gives us the tip for the total bill.
So you're basically taking this value that's an integer in the range of 1 to 10 and converting it to a percentage out of 10.
Yes.
Okay.
Yes.
And then you're taking that percentage of the maximum tip percentage.
Right.
So if they typed in 10, this would be 100% of the maximum 30% tip.
Yep.
And on the other hand, if they put in a 5, this would be 50% of that maximum 30% tip, or a 15% tip.
Yep.
Cool.
Totally. And then I just spit that out using the print line. And does that work? Yeah, that works, right?
Yes. In Java, this works.
In Java, that works.
In Python, this would not work.
Right, because I would have to cast it as a
string. You'd have to cast this as a string if you were going to concatenate. But Java, so this is one of the convenience features of the language, will allow you to concatenate onto a string a non-string value, and it will create a string representation of this value for you.
Okay.
And that's something that Java is designed to do. And it is pretty convenient. It is maybe a little confusing, but this comes in really handy, and we don't end up having to do that, explicit cast operation, and it keeps the code a little cleaner.
Gotcha. Cool. Yeah, so that's the tip calculator. Now let's look at something that I know a lot of people struggled with, which was the algebra tutor solution. And this one is a lot more complicated. So here I've got a bunch of different functions, and we'll take a little tour through them. Let's start at the very, let's start at main and walk through how that one works.
So main?
Start at main, yeah, where we were. Okay, so here's the outline of my program. I create a new scanner, and that's going to be my one user input. So I should only ever have, and this is a good rule of thumb for these Java programs that we write in this class. You should only ever have one single scanner that's attached to system.in. That's the user input one. So you want to put that as a either as a high-level thing that only goes in your main, or as a member variable or as a member of your or an attribute of your main class, so that you never create another one. So you should never have more than one new scanner system.in in your whole program. That's different than for the file inputs, because you would have to create a new scanner for every single file that you open. You can't really reuse a scanner for the file inputs. So that's a little caveat right there. I also keep track of a few things. There's the mode, and that's going to be the mode that we're doing, and I've got that defined as a couple of integers way up at the top of this program. And basically, it's what we're solving for. So we're solving for Y, we're solving for M, we're solving for I believe it's B, right? So those are my different mode types, and I've given them. I could just say 1, 2, 3, but I've given them these sort of names that make them easier to throw around, so I know what I can be a little more expressive with how I represent what mode we're in for the questions, the kind of questions we're going to be asking. Then I also keep track of how many problems the student has gotten correct over the entire run of the program, as well as the problems that have been attempted and the number of attempts in a particular mode. So the number of attempts there is going to be our, I can't remember exactly how that's used. Oh, that's whether I actually get a streak of, oh no. Yeah, I keep track of streak later. Yeah, streak is the number of
correct in a row.
Correct in a row. So that's like the winning streak type of thing. That name could probably be better. I would rather than having it be just streak, maybe I could probably call it winning streak. That would probably be more descriptive of what it actually means. And then percent correct is something that I use for reporting at the very end of the program. So the first function that I call is display menu, and we can go and look at that one real quick. So it basically just says spit out the available study modes: solve for Y, solve for M, solve for B, and quit. And it says 1, 2, 3, 4, enter a selection number, and that's all that function does. So it just prints out the menu in one big block. Notice that it doesn't actually take user input. The first statement after display menu is the part that does that, and that's the one that gets the mode. And then I jump into a while loop that says while mode is greater than 0. So as long as the user has put something in there and the mode is less than 4, so I'm looking for a mode between 0 and 3. If they select 4 or greater, then that I'm taking that as quit, and we just exit the loop, right? And that's when the program ends. So the first thing that I do is reinitialize streak and mode attempts, and I'm keeping track of how well those have gone. And then I have a loop that says while streak is less than 3, so as long as the student hasn't gotten 3 in a row, I do a print that says get 3 minus, get these more problems correct in this mode. And that was optional. It's a little bit of sugar in there that I threw in there because I thought it'd be nice for the students. And then I increment the number of problems that I've attempted. That's something that we've been keeping track of, as well as the number of attempts in this particular mode. Then I pass it, then I call inside of an if statement a function called solve problem. And what this does is it presents a new problem given the user input scanner and a particular mode. And remember, it's like solve for Y, solve for M, solve for B. And if this student gets the correct answer to that problem, that function will return true, and then it'll do the true part of this if statement. It'll increment problems correct, and it'll increment the streak. If the student got the problem wrong, that function will return false, and the else statement will be executed, and the streak will be reset, and I'll have to get 3 more in a row. If the mode attempts is greater than 3, then I show them a hint, and the show hint function just says something about what kind of problem they're trying to solve. So let's look at the solve problem function here. So the solve problem function does a few things, and basically what it does is it's a generic generator of problems. And what it does is it generates a problem by collecting 4 random numbers, y, m, x, and b. And notice that these are not yet related to each other. I'm just sort of filling in the blanks. Depending on which mode I'm in, I'm going to get the real answer that I'm looking for. And that's what the get target function does. And it gets the target answer given the y, m, x, and b parameters of a function and the mode. So let's look at what get target does. So get target says if I'm solving for y, the value that I'm looking for as input is the equation m times x plus b. If I'm solving for m, then the target is y minus b over x. And if I'm solving for b, then the target is y minus m times x. And I return that target answer. This is what we're looking for the student to give as an input to the answer. This is what we're looking for as the answer. So that gets the target answer. Then I display prompt, and again, the display prompt gives y, m, x, and b, and it has also takes the mode. So let's look at that one too. So this one says given these parameters, and if I'm in a particular mode, it will print out parts of the problem. So it says given if I'm solving for y. If I'm not solving for y, I want to print out y. I don't want to give them the answer. If I'm not solving for m, I want to print out m. If I never solve for x, so I always give x. And if I'm not solving for b, then I'm going to give b. And then I'm asking them to solve for a particular value. So if I'm in a particular mode, my target variable, which is just one letter that I'm going to insert into my prompt, I select which one of those based on the particular mode. So I say, what is the value of concatenated in the target variable and a question mark? So if we're solving for y, it should say, what is the value of y? If I'm solving for b, it should say, what is the value of b? And it kind of filters through all of these things and makes sure that we're not showing them the answer as it goes through.
Let's make a quick point here on what you're doing. So you've got a very generalized function here. So this function could be asking the user for the value of y, or it could be asking them for the value of m, or it could be asking them for the value of b. And correspondingly, for which one of those it's asking for, it's showing them the current values or the correct values or the given values for the other variables.
Yeah.
And this works whether they're solving for y or m or b. And the way that you were able to make this generalized function that works for all of these possibilities is by parameterizing those values. You've passed in a y value, an m value, an x value, and a b value, and a mode. And this allows this method to make some decisions based on that mode and produce the appropriate output based on the decisions. So the alternative to this would have been to make 3 separate methods that all basically do the same thing. So yeah. You've done a little extra work to save yourself more work from having to rewrite that same function. And so this is what's called a generalized function. And this is something that we're often aiming for as computer scientists. Rather than a specialized algorithm that solves one particular instance of a problem, we're looking for a generalized algorithm that solves all instances of problems of that category. So yeah. That's a good example of that.
And this took me a long time to get here. So my first attempt at solving this problem I wrote, you saw there were actually a couple of these types of functions here. You see this display prompt one and the one above it, which is the get target. Those are both generalized sort of functions, and I wrote 3 of them for each of these. So I would have 6 functions here that all do different things, and I would have an if statement on the outside that says, if I'm solving for y, then get target y. If I'm solving, then get target y, display prompt y. And if I'm solving for m, I would get target m and display prompt m and stuff like that. So I had less decisions, but I had 4 more functions than this, and my code looked really gross. I feel I've been doing this long enough that I feel uncomfortable when I see a lot of functions that are doing basically the same thing, and I want to sort of make them more generalized. I feel that pressure to make them more generalized. So it took a couple of rounds of rewriting this program to get this sort of compressed down to these generalized functions. And I feel good about how it sort of looks at this point.
Yeah, that's cool. And a couple of the tells, and you mentioned some of these, are if you find yourself and you feel like you're repeating yourself, like, didn't I just write this code, but the only thing I changed is I changed X to M, or I changed Y to B. Or if you find yourself wanting to copy and paste a function and make a couple of changes to it, then that's a good tell that might be a function that you can generalize, write one version of that function that meets all of your needs.
Yeah, absolutely. So where were we?
I think we were here in solve.
Yeah, we were solve problem. So my solve problem is pretty compressed, right? I can say get the target based on the mode that I'm in. I display a particular prompt, and then I can request an answer from the user using the scanner input that I created in main and passed into this function. Then I look and see if I check and see if the difference between the answer I'm looking for and the answer the student gave is less than a particular value, right? So basically here, I'm not looking for exactly the same answer. There's going to be some rounding, and people do the specific math a little bit differently. So as long as it's less than 0.1, the difference between these is less than 0.1, I'm going to consider that true, correct, and return true. If it wasn't the right answer, then I'm going to say incorrect. The correct answer is, and I give the student the target answer and return false. Right below it, we have the show hint function, and this was a really not super helpful set of hints, but it's basically telling the student that's using this program how the equation that they need to solve for particular thing, and it gives them for a particular mode, and it gives them a little encouragement to try and do this again, to try it again. And then I think that's most of main. Yeah, that's all my functions. And then after the student gets 3 in a row, after the user gets 3 in a row, I do a little bit of math to show the percent correct. So I take the number of problems that they've gotten right, multiply it by 100, and then divide that by how many attempts they made, and then print that out in a nice formatted string. Then I display the menu again and take user input for what mode they want. If, again, it's greater than 0 and less than 4, then the process repeats with a different mode. If it's greater than 4 or they give an invalid response, the program quits and says, thanks for playing, good luck. And that's my attempt at the program, at the solution.
Pretty good.
Awesome.
Pretty good. And this is a fairly sophisticated program. This challenge was a sophisticated challenge.
Yeah.
So this is probably the first challenge in this class where the complexity is such that you can't just directly break the problem down into a set of simple steps.
Mm-hmm.
You have to break the problem down into some intermediate steps, and then you have to break those intermediate steps down into simpler steps.
Mm-hmm.
And there's even, as you pointed out, an opportunity to generalize some parts of your solution. So kudos to all of you for your efforts on this very challenging project.
Yeah, definitely. Okay, let's go on to the other questions that we have today. I think it's Omar, but there's a student that asks if we offer any other courses on edX at this time. Unfortunately, no. We teach primarily on campus here at ASU, and we typically only offer one of these courses a semester, and so far CSE110 Programming for Everyone is our first programming class on edX, and it's the only one we have so far. So thank you. I'm really glad you're enjoying the class and that you like our sort of style in the class. That's really encouraging for us, and we put a lot of work into it, and we really love the class too. So we're glad you're having a good time.
I suspect there will be a follow-up to this coming to GFA at some point.
Yeah, definitely. So watch out for that. You might see us again in a later class, depending on when it goes. But there's we don't know when that will be. But if you want to take some other classes, go looking around for a data structures or data structures and algorithms or algorithms class that's taught in Java on edX or any other course website, and that's a good next step for your development.
So this next question is: creating objects done in order to make things easier for programmers, or can it be used to optimize processing as well? I feel like the first part of that question is probably the more correct answer. It's done more to make our job as programmers easier. It's a perspective on decomposing problems into components that are intelligible to humans. We interact with the world through objects, things like keyboards and mice and colleagues, and it's nice to be able to write programs in those terms. And I could define an object type in a program called a keyboard, and it can have the same sort of features, the same functionality and abilities that a keyboard can have. Or I can define maybe an employee database. I can define what an employee is in terms of first name and last name and social security number and address. And that tends to be much easier for us to reason about as humans than to think in the much more abstract, detailed terms of integer variables or string variables or float variables and stuff like that. So ultimately, I think if you really wanted efficiency and performance, we would probably not use object-oriented programming. Object-oriented programming is much more a set of techniques for making it possible for humans to solve complex real-world problems in software and manage that complexity in the software.
Yeah. But that's not to say that how you organize your information is not an efficiency thing, right? So when you get, if you decide to take an additional class on data structures and algorithms, depending on how you organize the information that you have available, if you have a lot of information, you can organize it in certain data structures that allow you to access it more efficiently. And objects are part of a way that we use to organize that information. And that can be a very, very powerful tool. But primarily, we don't need objects necessarily to organize information that way. We can do that in lots of different ways, but objects help us make it readable at its most core. So really, objects are for humans more than they are for computers to sort of organize our thoughts and how things are represented.
And what I'm about to say is a bit advanced, but the proof in that pudding is the fact that by the time your Java code compiles and runs, the objects are gone. Right. It is all just variables and stuff. So the object-oriented programming is a way for us to tell the compiler in a way that's easier for us to express what we want it to do in a way that's easier for it to express.
Yep. The next question is, this student has noticed that our programs have all been text input based. Will we cover other forms of input like the click here, which I think he means like GUI, graphical user interface type stuff or sensor-based input during this class? Unfortunately, no. I have a aversion to writing graphical user interfaces, especially in introductory classes, because they do not really represent most of the processes that students, or actually programmers, go through when they develop code. And the tools for writing GUIs do most of the work for you, and it's not that important for most of us. So when in a class like this that's focused on fundamentals, we avoid graphical user interfaces as well. As for sensor-based input, I think it would be really fun to be able to do this, but it's challenging for us to do that in the using the tools that we have. So that's an interesting idea. I mean, we can look into that for the next version of the class, see if we can simulate some sensors or something like that.
Or maybe even make some actual sensors available.
Yeah, make some actual sensors available, something like that. So that's a really interesting idea. You get to have something that behaves in the environment and against the, or sort of with the environment, very, very dynamically, which is interesting to see how your code translates into live behavior. And in our introduction to engineering class that we do here on campus, we have little robots that we have our students learn to program, and they behave off of the sensors, and you get to see how your code creates some certain behaviors in the real world, which is really exciting. So bringing that to you guys maybe is a more advanced version of that maze challenge that we developed at the very beginning, something like that. That's a really interesting idea, and we'll definitely keep that in mind.
Absolutely.
Yeah.
So this next question, is it possible to evaluate an input and determine its variable type based on it? For example, if input is a number, store it as a float, or else store as script, which I assume means text. Could this be done using overloading? So let's take this the first part. Is it possible to evaluate an input and determine its variable type based on it? So rather than variable type, let's use the word data type. Because variables have a data type, and we can store data of that type in the variable. So when you're talking about evaluating an input, so let's consider first keyboard input. So anything you type in on the keyboard, the only safe way to store that would be in a string, right? Now, so because if you try to extract it as an int and somebody types in BOB and hits enter, that's going to be a problem.
Yeah. And everything that you type in on a keyboard starts out as a string too, right? So the character 6 is not the same as the value 6, right? And we looked at that way back in the data types, computers and data section, where we had the ASCII ASCII table. That's a translation between the number that represents a character and its actual value. So those are two different things. So everything starts out as strings, and that's probably where you would start with something like this.
Right. And I think this is where the student's question is going. If you don't know what the user is going to type in, and the user can type in anything they want, how do you safely extract that and manage that? Because if they type in Bob when you're expecting an int, that's a problem. And the answer to this question is a technique that we call parsing. So we would collect that input as a string, which is safe. All sequences of characters can be safely stored in a string. And then we would look at the characters in that string using some of the techniques that we're already familiar with. We could use a loop to iterate over the individual characters and look at the characters. And if all of the characters were digits, 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9, then we could say, well, this looks like an int. It's probably safe to convert this to an int, store it in an int variable. Or if we found a decimal point in there, we might say, okay, this looks like a float. So it is possible to do this, but it is sophisticated and gets tricky. But this is precisely what the scanner is doing for you. When you use the scanner in Java and you say next int, it's reading those characters out of there as characters, as part of a string, and then parsing that as an int. And the way that it's set up is if that fails, it crashes your program, which is weird, but if you stick with this, you'll come to find that that's appropriate. It's appropriate for code to crash your program. When you ask the computer to do something that it's not able to do, the only appropriate thing to do is to crash.
Right.
It shouldn't pretend like that was okay. It shouldn't guess like maybe you meant this.
Yeah.
It just has to say, look, what you wrote here didn't work. You need to write something else.
Yeah, and way at the end of the course, after our last sort of graded unit, there'll be some extra material on ways that we can prevent it from crashing and handle those what we call exceptions, those things where we expected something to happen that didn't happen. How do we handle that cleanly rather than letting the program destroy itself? Yeah.
We want to discuss this part of the question here. Could this be done with overloading? So really quickly, let's unpack the term overloading. So what we're talking about when we talk about overloading, or more precisely method overloading, is the ability in a language like Java to write more than one method with the same name. So I might have a method called, get user input, and I could write multiple versions of that method as long as they were different in their argument list. Right. They would either have to take a different number of arguments or a different data type of arguments, or the types of the arguments would have to be in a different order. Maybe it takes an int and then a float. I could make another one that takes a float and then an int.
Yeah.
And that would be method overloading. Classic examples would be things like, if I want a method that will tell me the largest of two numbers. It would be nice to be able to tell the largest of two ints. It would be nice to be able to tell the largest of two floats. And it would be nice to be able to tell the largest of two doubles. Rather than having to make three differently named methods, like largest of two ints, largest of two floats, largest of two doubles, I could just make three different methods all called largest. One takes two ints, one takes two floats, one takes two doubles.
Yeah.
And this gives us a nice convenient namespace where if you want to get the largest of two values, you just call the largest function and give it the two values, and it figures out which one of those methods to call based on the data type of those values. So I'm not sure that applies directly to this particular problem.
Well, I see where I think Bill is the guy that asked this. I see where Bill is going, because he's thinking, if I take a generic input from string and I define a bunch of functions that have different input data types, and I just pass that string to that overloaded function, the computer will figure out which one it is. But that's not the case, because it's always going to be, as far as the computer is concerned, you're always taking in a string or whatever you asked for. If you take in an int, it's an int. If you take in a float, it's a float. If you take in a string, it's a string. And the computer doesn't figure out during runtime which one you are trying to call. It figures it out during compile time. So you can't make that, you can't use overloading to determine what the type is when it's being taken in as user input. You have to either figure it out using the parsing approach that we talked about, or make the scanner do it using next in float, or next int, next float, or just regular next to get the string. That's
right.
Yeah.
So and I think the other piece of that is it's not possible to have overloaded methods which differ only in the return type.
Yes.
So if you've got a method that takes a string, you can't have one version of it that returns an int and another version of it that returns a float and another version of it that returns, a double. Because the only way the runtime system can tell which version's being called is by looking at the argument. And if the argument is always string, it doesn't know which one. Yep. There is one weird thing you could do, but it's just going to put you into a new quagmire. And that is, you could return a value of type object. So in Java, everything is an object. And we'll talk about why this is towards the end of the semester. It comes from a thing called inheritance. And so if you declare a variable of type object, you can store whatever you want in it. Mm-hmm. And so if you have a method that whose return type is object, it could theoretically return anything. But the problem with it is when you call that method, you don't know what you got back.
Right.
All you know is you got back a thing.
Yeah.
And now you're in basically the same problem that you were in when you had this string and you were like, is it an int? Is it a float? At least you knew that was a string. Now you got a thing and you don't know what it is. So
right.
Not sure that solves the problem.
So the next question is, do programmers ever write multiple functions or methods to do the same thing and then have a way for the computer to determine the optimal route for processing? I'm not really sure exactly what Bill is going for in this question. Do you have an idea?
Well, I can make up something. So let's say that same thing is sorting a list of values.
Yeah. Okay.
So there are lots of different ways to sort a list. And for some lists, one way of sorting might be more efficient than another way of sorting.
Mm-hmm.
So we might have different methods that do the sorting in different ways that are more or less efficient for different specific lists. So then the question becomes, is it possible to allow the computer at runtime to decide which method is the most efficient method for sorting this list?
Yeah.
I think it's possible.
Yeah.
I don't think it's simple.
No. And it does happen sometimes. The most obvious one that I can think of is that sorting example. Is there are certain algorithms that work really well. They're very fast and very simple on very short lists, very short sets of data. And there are other algorithms that are not so good on short sets of data, but they're really great at big sets of data. So you could have something that says, if my list is less than 10 items, then use this really dumb sorting algorithm. It's dumb and fast for small sets. And otherwise, use this really complicated algorithm that's really fast on large sets. And if you're doing a whole lot of these things, then you want as much performance as possible. So that's definitely possible. Those are things that really happen. But there's a rule in programming called or not a rule, but it's like a rule of thumb. And the idea is get it to work now, optimize later. So never focus on optimization. Just focus on functionality. Once it's running, you'll be able to figure out what you should spend your time on making it faster. So that's where most of it goes, and it's only like that 10% of the overall program is the part that takes up most of the computation. And you don't need to optimize everything. You just need to optimize that one little 10% of the program. So don't focus on. Make sure you're not focusing on optimization. It's a good thing to know eventually, and you'll see it from experience and working with higher level programs and stuff like that. But it's not a thing that really a lot of programmers do very often. They just make stuff work and then spend some time optimizing later.
Yeah, correct code and code that's testable and debuggable, code that you can prove is correct, or if it's not correct, you can fix it, is worth a lot more than fast code. Yeah. Especially if the fast code isn't correct. And if the fast code is complicated and it's not correct, it's very difficult to figure out how to make it correct. So it's always easier to start with code that works and figure out how to make it more efficient than to start with efficient code and figure out how to make it work.
Yeah, totally.
All right. How does multiple core processing work? Is this something your code has to account for, or does an operating system handle it all by itself on a lower level? Okay. The operating system is not going to handle it itself. Nope. There's going to be some language level, some program level control going on there.
Yeah. So basically, what happens when you run a program is what is basically called a thread is spun up by the operating system, and a thread is a thread of execution. It is one sequence of instructions that's running on one processor at a particular time, right? And the operating system keeps track of that thread, that the execution of your one program. If you want the operating system to take some task inside of your program and run that on another processor, you have to create, your program has to ask the operating system to create another thread that the operating system can then push to another processor and run at the same time. This is a very advanced programming technique. They call it multi-threading, and all operating systems have specific calls for making that happen. And we will really, again, only do it when we really want to optimize something, or we want something to happen in the background as far as the program is concerned. And there's a lot of really crazy stuff that can happen. If you want the two threads to communicate, if you want to send data back and forth between them, if something needs to happen and you're doing all these weird behaviors, there's 1,000 different ways to do it. When you see a program that works for example, Windows, but not for Linux, it's probably because it's using operating system calls that handle stuff like that. And it's all specific to an operating system. So the multi-threading for Windows is very different than multi-threading for Linux. And that's kind of the differences between them. And that's why you have to write a program for a specific operating system rather than just writing one generic program for all operating systems. Java helps with that. Java has a threading interface that sort of abstracts away what the operating system is. So you can look at that if you want later on. Again, it's a very advanced technique, and it's like right now we're struggling to think about one program, much less like 10 programs that are all running at the same time. So it's a whole other level of programming. You might see, if you want to learn about this sort of thing, you might see classes on operating systems or multi-threading, and those are really good things to look at, is to see what you can pull from the operating system to do really advanced, really high performance programming.
It's cool stuff, though.
Yeah.
All right, this next question is a big one. What is quantum computing, and at what level of hardware or software is that determined? Okay, I'm going to fess up here. This is a little outside of my area of expertise.
Okay, so I'll take a stab at it because I'm not good at this either. But let's do the second half of the question first. So quantum computing is a new architecture for computing that is not even, well, it's very fledgling. Like, it's only started, I think there's only been there's only been research level quantum computers available for the last 10 years or so, something like that. So it's very, very new. And the idea behind it is, rather than, so all of our normal computers, they run off of certainty of bit, right? So you have either a 1 or you have a 0, right? And it's either one or the other. It's never both or somewhere in between, right? So it's true or false, and that's it, right? All of our computing architecture computing environment that we deal with on a day-to-day basis is based off of that digital binary value, right? So quantum computing allows a bit, and instead of a bit, we have to make something that's called something different. They call it a qubit. A quantum bit can take on any value of a sort between 0 and 1. And it gets really, really crazy. And basically, it's a probability of being 1 or 0 somewhere along that spectrum.
Well, isn't it weirder than that? Isn't it a combination of 1 and 0 and all the values in between? So yes. It's a probability distribution.
True.
Right? So yes. All the values between 0 and 1, for each possible value between 0 and 1, and there's an infinite number of them.
Yeah.
It has a probability of being that fraction of 0 or 1.
Yes.
And the total probability is 1.
Yes. Right. Yeah. And so rather than, that's a great place to sort of make a contrast, is modern typical digital computing is deterministic, right? We know that if we add 0 and 1, we will get 1. If we add 1 and 1, we get 2, that sort of thing, right? In quantum computing, 1 and 1 does not equal 2 necessarily, right? So instead of just 1 and 1, you have a mixture of probabilities, and by combining them using quantum operations, we get a new mixture of probabilities. And basically what that allows us to do is to explore a lot of different possibilities in a very quick way. using this new fundamental architecture. It's really complicated. Very few people understand it. I don't understand it. I don't understand it. I have a very like pie in the sky, fuzzy, foggy view of how it works. And I've taken like quantum physics classes and stuff like that as part of my undergrad and grad work. And I didn't, it's beyond me. And it's because it's a brand new field. The people that really know this stuff are building these machines, and they aren't even sure how to program them yet, right? It's a really, really brand new field. It's very exciting because a lot of really challenging problems for digital computers, for deterministic computers, might be really simple for these quantum computers. So that's really exciting avenue of new development. To show you sort of how advanced we are now versus how advanced these quantum computers are, there are literally billions of deterministic transistors in the machines that you have in front of you. Like the CPU of your laptop or your computer or your phone has billions of objects that of transistors that allow us to find answers to problems in a deterministic way. I think the record now is 72 qubits, and that's a Google quantum computer. Google is developing its own quantum computer, and they've got 72. So we're many, many orders of magnitude away from being as complicated as the problems as the computers that we have now. They're very, very new, and it's a brand new field. So it's exciting to learn and see what's going on there. It's more likely that you guys out there will be able to teach us about quantum computing in the future than we'll be able to teach you guys, because you'll be growing up with these new technologies, and we're kind of like stuck in the deterministic age, I guess, something like that. Awesome. And then the last question is from me. Have I made any cool robots recently? Trying to think of the last robot that I made.
I saw you working on that PID controller for the satellite dish.
Yeah. So I mostly, when I build stuff now, it's mostly when I build stuff now, it's for demonstrations for my classes. So I have an embedded systems class, and it's kind of like a robotics class, but we're learning how to program microcontrollers and Arduinos and all kinds of stuff like that. And as I go through the topics, I'm building little demonstrator application things that I can use during lecture, and we can use during activities and labs and stuff. And what I'm working on right now is something that it's a satellite dish simulator. And the idea is to write a program that just keeps it pointed at a particular angle of the sky under a lot of different conditions. Like I'm going to blow on it to simulate wind, and I'm going to like push on it and throw things at it and all kinds of stuff like that. And we'll see how it responds. And it's a really simple little thing, but it demonstrates a complicated concept and a complicated software design that we're learning in class. So that's the kind of thing that I build typically now is little demonstrator sort of robots and stuff like that, which is a lot of fun. You get to tinker a ton.
It's the essence of robotics, right?
Yeah.
Which is some unit of computation, some unit of sensing, and then some unit of actuation.
Yeah.
Right.
Yeah.
So make some sensor inputs from the environment, compute some action to take, and apply that action through motors and other devices, and then repeat the process.
Yep. And there's a million different ways. It's a whole other discipline, is figuring out how to architect your software to make that respond to different conditions and stuff like that. That's the kind of stuff that I'm all about, is that sort of real-time response sort of stuff. So
cool.
Yeah. So great questions today, everybody. Thank you so much. Nikesh, I see the comments that you've been leaving in the chat room and on the discussion boards. We'll keep at it. It sounds like the tests on your program are running, but we need to see if we can find a little more detail to help pinpoint where the problems you're having are. So keep posting. I'll ask for more detail online, in the discussion boards, and we'll keep at it. Everybody, you guys are doing awesome. The Pepper's Pill Mill challenge is very challenging, and you guys have stuck with it. You're making great progress. Keep it up. It's that struggle where you learn things. You guys are all struggling a lot, and you're learning a lot, I'm pretty sure. So if you have questions, please post them in the discussion boards. We're there to help. And we'll see you guys on the flip side.